Hi everyone, we're continuing with the basic cosecant and secant functions. As far as symmetry goes, remember that the old sine function was odd, so its reciprocal function, the cosecant function, is also odd, meaning that both graphs have the following property. They have symmetry about the origin. If you rotate either graph 180 degrees about the origin, you get the same graph. For the cosecant graph in red, for example, this red up U rotates to this red down U. Likewise, this red down U rotates to this red up U. Now the old cosine function was even, so its reciprocal function, the secant function, is also even. Those graphs are symmetric about the y-axis. The cosine graphs and the cosine graph and the secant graph are both symmetric about the y-axis. Okay, now what about vertical asymptotes, VAs? Well, take a look at cosecant of x, which is, remember, the reciprocal of sine of x. We have a VA when cosecant of x is undefined. And cosecant of x is undefined when sine of x, the bottom here, is what value? When sine of x is 0. So cosecant of x blows up when sine of x down here is 0. Well, where is sine of x equal to 0? If you look at the unit circle, sine of x corresponding to the y-coordinate on the unit circle corresponds to this east point and this west point. And these points correspond to integer multiples of pi. 0, pi, 2 pi, 3 pi, 4 pi, and so forth. And they're opposites, like negative pi and negative 2 pi. So we have vertical asymptotes if x is of the form pi n for all integers n. Likewise, the domain for the cosecant function is going to be the set of all x in the reals where x is not of the form pi n for all integers n. Now you might find this familiar. The domain for the cosecant function is the same as the domain for this cotangent function. And why is that? Because, look here, cosecant of x by the reciprocal identities is 1 over sine of x. Now, we had a problem when sine of x was 0. What other function has the property that when you tear it apart, you have sine of x on the bottom? Well, cotangent of x, which by the quotient identities equals cosine of x over sine of x. So cotangent of x and cosecant of x are both undefined. They both blow up when sine of x, this bottom guy, is equal to 0. So it makes sense that they both have the same sets of VAs, and they both have the same domains. If you look at the graph of y equals cosecant of x, up here, the VAs are at x equals 0, pi, 2 pi, and so forth. These were the same VAs as for y equals cotangent of x. Same VAs, and also the same domain, the domain for the cotangent function, the domain for the cotangent function was the set of all values, real values of theta that were not of the form pi n. Likewise, the domain for the cosecant function is the same. The domain for the cosecant function, all real values of x in this case, where x is not of the form pi n for integer n. Similarly, let's take a look at the domain for secant of x. Well, secant of x, by the reciprocal identities, secant of x is equal to 1 over cosine of x. Well, secant of x is undefined. It blows up when cosine of x equals 0. And what other function had cosine of x in the bottom when you tore them apart? Tangent of x was sine of x over cosine of x. Both tangent of x and secant of x blow up when cosine of x is 0. So secant of x and tangent of x have the same domain. We have a problem when cosine of x is 0. Cosine is the x coordinate. Where is x coordinate 0? At the north pole and the south pole. So both secant and tangent have a problem when x is of the form pi over 2 plus pi n, where n is integer. It can be written like this. Now notice that when you write the domains and the ranges for the 6 basic trig functions, that's a great exercise, these sets tend to pair up. Again, the domain for cosecant of x and the domain for cotangent of x, they're the same. Likewise, the domain for secant of x and the domain for tangent of x, they're the same. Up here, we have a problem when sine is 0. Over here, we have a problem when cosine is 0. For example, at pi over 2. For secant of x, like for tangent of x, we have VAs at x equals pi over 2 plus pi n. So for this graph over here, we have VAs, like for tangent of x, we have VAs at pi over 2, 3 pi over 2, and so forth. And therefore, the domain consists of all real values that exclude those places where we have VAs, that exclude pi over 2, and so forth. Now, what about the range? It turns out that the range for secant of x and cosecant of x are the same. These two pair apart. The ranges for the two functions. It's this over here. It's a high-low game. And why is that? Let's take a look at cosecant of x up here. Look back at the range for sine of x. The range for sine of x goes from, these are y coordinates, goes from -1 to +1. The closed interval from -1 to +1 is the range for sine of x. That's the range for sine of x. Now, if you look at the range for cosecant of x, we want the y coordinates that we pick up on the red graph here. And it turns out that we take the range for sine of x and we turn it inside out. We get these high positive values and we get these very negative values. Over here, we get all positive values greater than or equal to +1. Down here on the down U pieces, we get all negative real numbers up to and including -1. The range for both cosecant and secant, again, we have the positive numbers from 1 off towards infinity, the negative numbers from -1 down towards -infinity, but remember, we follow the real number line. So we indicate this range as parenthesis, -infinity. In fact, you could think of it as a vertical axis, from -infinity up to -1, from -infinity up to -1, and then from 1 up towards infinity. A union of these two intervals, high-low. These positive values, union with these negative values. These positive values, union with these negative values. High, low. We're turning the range for sine of x inside out, like so. Now, cosine and secant just give horizontal translations of these, but the picture with the y coordinates, that just translates over. So we have the same range for both sine and cosine, and the same range for both cosecant and secant. Again, it's the high-low game. Cosecant of x and secant of x have the same range. It's a union of two intervals, these positive values and these negative values. Notice that what number is not in the range? What number in here is not in the range? 0. 0 is not in the range of either cosecant or secant function. Cosecant of x and secant of x are never 0. And that's helpful. For example, if you have a trig equation, you can easily divide both sides by cosecant of x without things like domain issues. All right. Next up, we're going to transform these functions and these graphs next time.